Hello jitter fanatics, and welcome to the second tutorial about JIT.GEN. In this tutorial we are going to see the JIT.GEN object finally, and the GGL mesh. We are going to create a shape that looks like this, and then we are going to see also some concepts about vectors, and that's because in JIT.GEN we can work with vectors. So it's useful to know what a vector is, and will be totally useful to understand how to work with the JIT.GEN and the three-dimensional shape. So let's start from scratch and see what we have got here. So we have a GGL grid shape, shape sphere, which is the default shape, dimensions 200 by 200, and matrix output 1. So this means that this object, instead of being rendered in the window, will output the matrix that we saw on the last tutorial. So if you remember, in the last tutorial we used the JIT unpack to extrapolate the single planes that we are interested in. For example, with just one output and the jump 3 attribute, we are going to get just the x, y, and z first three planes. So the first three planes that contain those coordinates. Then we have JIT.GL mesh here. JIT.GL mesh is a visualizer for vertices. So if we feed it with a matrix containing some points or some numbers, it will visualize these numbers as vertices on the window. As you can see, it has a bunch of attributes, color, lighting, and smooth shading that are the same for the grid shaped object. Then it has this autonormals attribute, and the autonormals attribute calculates automatically the normals for the GGL mesh. So we can either feed the GGL mesh with a normal array, so a normal matrix, or we can use the autonormals attribute, which will automatically generate normals. So let's create a JIT.GEN object. Let's connect it with the unpack, and let's connect his other output with the GGL mesh. As you can see, a sphere is appeared on our window, and let's take a look at what we get inside its JIT.GEN. So as you can see, we have an input, two inputs actually, input 1 and input 2, a plus operator, and an output 1. So this is how JIT.GEN looks like when you first create the object. So, as you can see, it works like Max. It has graphical objects that you can connect with cables, but the objects are a bit different as the objects in Max. For example, there are no cold inlet, everything has hot inlets, and JIT.GEN only works with matrix streams. So by default, the JIT.GEN will sum the input 1 with input 2 and output the result. So what does it mean? Let's create JIT noise, for example, 3, flow at 32. Let's make it just 10 by 10, and let's connect it to the second input here. Then let's create a bang. Let's bang this matrix and see what happens. So our shape has been displaced according to the noise, but we have a 10 by 10 matrix here, and here we have a 200 by 200 matrix. So how does this work? So by default, JIT.GEN scales automatically the dimensions of the matrices that comes in the right inputs according to the dimensions of the matrix in the most left input. So this matrix has been automatically converted in a 200 by 200 matrix, and its values are being interpolated. So let's take a look at what is actually happening inside JIT.GEN. So the three planes of the matrix that comes in are actually x, y, z coordinates for every vertex. So if you remember how a JIT matrix is made, this is like a grid, and every value is contained inside a cell inside this grid. So this is a cell of the grid, this is another cell. And this whole rectangle is a plane of the matrix. So, and the first plane in our matrix is the x dimension. Then there is another plane behind that. Let's say that is behind that, that contains other cells. It's another grid basically that contains other cells. And this is the epsilon plane. Then there will be another plane that is the z plane. So these three planes inside the matrix contains cell, and every cell is a value that it's actually a coordinate in a three-dimensional Cartesian world. So the first plane is the x value, the second plane is the epsilon value, and the third plane is the z value. So here we have our three coordinates. So every cell contains these three planes, which are actually the three coordinates. And we can say that also the three planes from the JIT noise are actually x, y, zeta coordinates. So we are summing to every x, the x from the noise, epsilon to the epsilon, z to the z. If we connect it like this, we can see actually the JIT noise values represented as a point in space. So you can see that they are just in the positive x-axis, positive y-axis, and positive z-axis, because they are from 0 to 1. While the JIT grid shape by default goes from -1 to 1 on every axis. And this is also how the JIT.GEN mesh represents shapes. So that 0 is the center, and then there are negative and positive directions for the points. So let's connect it as it was before. Okay, let's now completely delete the input 2 and the plus operator, and let's look at another feature of the JIT.GEN. So there is this feature is called SWIDSLink, and in fact we have an object called SWIDS inside the JIT.GEN that doesn't exist inside the normal max environment, and this object allows us to extract the single planes from the incoming matrix. So for example, if I say 0, the SWIDS 0 will extract just the first plane from the incoming matrix. In fact, if I enable the render now, the shape disappeared because it's being rendered as a triangle grid, and we don't have any triangle grid now. So if I take another SWIDS object and say SWIDS 1, now I can extract the second plane, which is the epsilon position, and I can do something like this. Can create a back object, and then can connect the SWIDS 0 to the first input of the back object, SWIDS 1 to the second input, and then connect it, and then I have a flat sphere. So what have I done here? I've taken the x plane. Let me actually reset the handle here. So I've taken the plane that contains the x values. So I have all the x values for this shape. And then the plane that contains the epsilon values. So I have all the epsilon values for this shape. But I don't have any z values because I don't have any z position. So let's take a look at this object. It's called vec. And this is what I was talking before, that in JIT.GEN we actually can use vectors and vectors operation like dot product, cross product, the length of a vector. All these kind of operators, they are vector operations. So let's make a pause here and see what a vector is. So let's take a look at this image, at this poorly drawn image. What do we have here? We have 2 points in space. So this is one point here, and this is another point here. The first point, so point 1, has coordinates 1.5 and 1.5, and point 2 here has coordinates 3 and 4. So a vector is a mathematical, actually it's a geometrical object that represents a quantity that cannot be expressed with just a number. So for example, let's say we have the 8 of a person. This is a person, and it's 8 here. Can be represented with a quantity. For example, let's say this person is 10 meters tall. And this is a single number that represents a quantity. But for example, if we have the wind, we can't represent a wind like with just one number. And we can't say we have a wind of 40. We have to say we have a wind of 40 that goes in direction north east. So the wind needs a number to represent how strong the wind is, and a direction that tells us which direction is the wind blowing. So this quantity can be represented with a vector, because a vector represents exactly a direction with a magnitude. So the magnitude is the how the vector is strong. Let's say what's the length of this vector, which is the length of this arrow here, and the direction is represented by this arrow. But mathematically, how can I know which is the head of the vector and the tail is called the tail? How can I know this mathematically without having a graphical representation? Well, the vector always points in the direction of the head, so it goes from the tail to the head. So if I have a vector that has its tail at 1.5 and 1.5 and his head at 3 and 4, the components of this vector will be, so its components will be 3 minus 1.5, so x minus x head, so this is x head minus x tail, and then I have epsilon head, which is 4 minus 1.5, so epsilon head minus epsilon tail. And this will give me the components of the vector, so 1.5 and 2.5. So since these are positive numbers, I know that this vector goes into the x epsilon positive axis. Let's put this here. So this vector goes into the positive x direction and into the positive epsilon direction. If this number were negative, I would have known that this vector was going in one of these directions, into the negative part of the axis. So this is what a vector is and how can be represented. So the length, as we said, how this arrow is long, this is the length of the vector, this length here. And the length can be represented with the Pythagorean theorem, because actually is exactly that. It's like the hypotenuse of a rectangle triangle. So let's say that this is the x-axis of the triangle, and this is the epsilon axis of the triangle, and this side is exactly the difference between the x of the head and the x of the tail, and this axis is exactly the difference between the epsilon head and epsilon tail. So this is the hypotenuse of this triangle rectangle. If you remember, the hypotenuse is calculated as the square root of the component of the triangle squared, the x component of the triangle squared, plus the epsilon component of the triangle squared, and this gives me the magnitude. So that's the hypotenuse or magnitude of the vector. So this is the length of the vector. A vector here is represented as with two quantities for a x epsilon space, but if we have also a zeta axis here, I can also have, so let me write z, I can also have a vector that goes in 3 dimensions. So a vector that goes like this, for example, in 3 dimensions. Let's imagine that this is a 3-dimensional space. This vector goes in 3 dimensions, and it's a bit like this. So I can easily add another component to this vector and create a vector that is represented in 3 dimensions. So this is exactly what we have inside our JIT.GEN world. So let me create another image. So the position of every vertex of our shape, so let's say this is our shape, every one of the vertices of the shape is actually a vector. It's called the position vector because it has no head, it has no tail, it's just the head of the vector. So by default, the tail of the vector that as its head the vertex is the zero position. So these are called position vectors, which have by default the center of the system as a tail. So these are our vertices that we have inside the JIT.GEN grid shape object. So the matrix output from the JIT.GEN grid shape contains these vertices that can be interpreted as vectors and are interpreted in fact as vectors inside JIT.GEN. So back into JIT.GEN, back into Max, and back into JIT.GEN, let's also take the zeta axis. Let's do something like this, and let's compose our three-dimensional vector. So now every vertex of the shape, we can visualize the vertex by using the polymode attribute for a GGL mesh object. So every one of these points here, as I said inside my tutorial about OpenGL, my first tutorial about OpenGL, you can go deeper, you can see this concept explained also better. But basically, every one of these points is a vertex contained inside a JIT.GEN grid shape, and it's actually a vector that has its head on this point and its tail on the center of the grid shape. So on the point here, when I move with the handle, you can see there is a center of axis, and this is the center of the Cartesian system in which the grid shape is created, which is the reference for the grid shape. So once we know that, we see that we can create vectors inside JIT.GEN basically as we want. So we are extrapolating here the different components of the vector. Actually, we can call them also x, y, and z. So the width object accepts like 0, 1, 2, and so on syntaxes, but it also accepts the syntaxes x, y, z, and w, but not more than w. So if we are working with the three-dimensional coordinates, we can use this notation here. If we are working with more planes than 4, then we have to use numbers. And it also accepts the RGB and notation for colors. So I could also write here alpha, red, and green, because actually in the matrix world, the alpha channel is the first plane of the matrix. So, but let's stay with the x, y, z notation because we are working with coordinates, so it's better to use the x, y, z notation to not get confused. And let's make something nice. So in JIT.GEN, we can communicate with Max. Actually, we can communicate from Max with JIT.GEN by creating parameters inside JIT.GEN. So inside JIT.GEN, I can create a param object and give it a name and a default value. So now if I pass a message, so if I do something like this, and I pass it, I don't know, some floating point values with the clocker object, let's divide this by some big number. So the clocker object gives me the milliseconds, gives me the seconds actually passed since the program is running. So I can divide it with a big number and get the milliseconds. I get the seconds, sorry, it gives me the milliseconds actually, and I can divide it with a big number to get the seconds. And now I can use these values inside JIT.GEN. And every one of these values will be added to the single values in every cell of this matrix. So for example, let's say that I want to take the cosine of the zeta position plus time. So I can also create a plus operator and I can either connect it with the param output, or I can write directly the name of the parameter inside the plus operator, which is pretty cool. And I can connect it here. So if I activate now the clocker, it will do something like this. That's pretty cool. So another thing that I can do is to multiply that by 2p, so 2 pi, and get the full phase of the circle, and get something like this. So the full phase of the cosine, and get something like this. I can actually multiply it for something bigger also, and get more waves. So now I'm the frequency, it's like I'm making the frequency bigger with this super high frequency. If we multiply by 3, it's still okay. Then I can multiply, for example, this quantity by some value, and then add this quantity back to the original zeta axis. So like that. And then I have this effect here. But still I kind of like the first effect. So this one is pretty cool. Okay, but you got the idea. You can basically work on every single vertex of this shape on the JIT.GEN using some vector arithmetics and some vector tricks that we are going to see in the next tutorials. And basically you can really go crazy and modify these shapes as you want by using some simple math as we did here, or using some vector calculations. You can really get some interesting effects. So I hope this tutorial was clear. I hope you got most of what I said, and if you have some questions, please write me. If you want, you can also support me on Patreon. That would be great. The link is in the description of the video. In my Patreon, you can also get some more patches that I've done, and maybe take a look also to my website, which is called www.federicofoderaro.com. There you can find all my works and all the stuff I have done with Max. And so, okay, see you into the next tutorial. Ciao.
It's a good show.